Our next speaker, he's a principal engineer at JUXT, and he's also head of the AI practice, which is an internal expert group that tracks emerging trends in AI. Henry, up until he joined JUXT recently, was CTO at Reg Genome, applying AI to regulatory intelligence. So he's an expert in AI, he's an expert in regulatory technology, and he's also been a long-term friend of JUXT. In fact, legend has it that Henry paid the first ever JUXT invoice.
Welcome.
So please give a warm welcome to Henry Garner.
Thank you. Thank you. Imagine this scenario. A patient rushed to hospital with a racing heart, a mottled and painful leg, and dangerously low blood pressure. The diagnostic team launch a comprehensive investigation. Angiograms, ultrasounds, CT scans, and autoimmune tests all come back negative. Then, a junior team member notices something crucial: faint scars on the patient's forearms consistent with self-harm. She's suffering a chronic eating disorder and the toxic effects of a particular emetic. She needs an immediate heart transplant. Within days, a donor heart is found and the surgery succeeds. But these doctors saved a life by breaking the law. They violated Title 42 of the Code of Federal Regulations, Part 121. A donor heart was only made available immediately because the patient's eating disorder was not disclosed on the transplant application. This deliberate falsification exposed the lead physician to serious consequences and risked the loss of the hospital's transplant accreditation. The team had faced a difficult dilemma: save the patient's life or follow the rules. This is the basic plot of Season 1, Episode 14 of House, MD. So for those who don't know, Dr. Gregory House is a genius diagnostician. He's capable of solving cases others cannot. However, he operates with profound ethical blind spots, treating patients as intellectual puzzles rather than human beings, and medical ethics and hospital protocols not as safeguards, but as irritating barriers to his process. Dr. Lisa Cuddy serves as Dean of Medicine and faces an extraordinary challenge. She doesn't merely supervise him administratively, she functions as his ethical guardrails. She must constantly calibrate how much latitude to grant him. Too little restraint, and he's an existential threat to the hospital. Too much restraint, and patients lose access to his unconventional solutions. Each day brings a fresh balancing act between enabling his medical innovations and enforcing professional standards. Now, the principles of medical ethics aren't a recent invention. They stretch back at least to the 5th century BC and the Hippocratic Oath, which originally contained rules like, I won't administer a lethal drug to anyone, even if I'm asked. But a century later, Aristotle produces a significant early work on ethics. His focus wasn't medicine, but something even broader. What does it mean for humans to live well? For him, the highest purpose of life is to find a way to flourish, which he defines as the act of living virtuously. There are 16 virtues in all, and each is situated between two vices. So for him, the challenge wasn't to adhere to rigid rules, but to strike the right balance. He used the word phronesis, which is usually translated as practical wisdom, to describe this character trait of being able to navigate life's challenges with sound judgment. Martha Nussbaum says this of phronesis: practical wisdom sees that part of the good person's equipment for good action is the ability to perceive particular features of complex situations. And phronesis is experiencing a revival in the, this is Google Ngram's viewer, plotting the usage of words over time. In the post-war period, the increasing power of medical technology in particular, such as organ transplants, but also life support machines and genetic engineering, have raised these new questions about when life begins and ends, quality versus quantity and resource allocation. And the field of bioethics has crystallized to help practitioners systematically decide between potentially conflicting values. And we're all accustomed to weighing competing benefits. The engineers in this audience will call them trade-offs. And foundational methodologies like Agile express them this way. While there's value in the items on the right, we value the items on the left more. But notice how Agile's core values prioritize human elements, individuals and interactions, customer collaboration and responding to change. Recognizing that many of our trade-offs aren't just technical, they're about people. And the Cogblink's judgments in other areas have required or encouraged regulators to implement what they call principles-based regulation. The FCA has these 12 core principles. The most recent addition is consumer duty, which says that firms must act to deliver good outcomes for consumers without specifying exactly what or how that's to be achieved. And now this approach promises a light touch style that can keep pace with fast-moving sectors like financial services and technology, where rigid rules quickly become obsolete. But the theoretical advantage don't always translate into practice, because the trend is definitely towards more regulation. And despite favoring principles-based regulation prior to 2008, regulators came to see its flexibility as a weakness after the financial crisis, because firms could follow principles like maintain adequate capital for themselves, but still contribute to systemic risk through complex interdependencies. And so after the crisis, regulators responded with detailed rules instead. The Dodd-Frank Act began as 848 pages and subsequently generated over 22,000 pages of implementing rules. So despite good intentions from regulators, dynamics like these have created an overwhelming regulatory landscape, and a recent survey found 58% of compliance professionals cite keeping up with regulatory change as their biggest challenge. Technology firms are building products to help. RegGenome is an example from Cambridge University. It's a spin-out that works with regulators to create standardized classification systems for regulatory obligations. They use AI to organize regulatory data into structured information that both regulators and businesses can easily understand and compare across jurisdictions. And Johnny is in the audience. He's head of product at RegGenome. And before joining JUXT, about 9 months ago, as you heard, I worked as RegGenome's Chief Technology Officer. I helped guide the technical team, turning the academic research from Cambridge into a commercial product. And we specialized initially in financial services regulation and needed to capture everything that compliance professionals might need. Laws, rules, and regulations, of course, but also reports, guidance, and enforcement actions across over 100 different jurisdictions. And financial regulation, as you know, is not centralized. Every jurisdiction has multiple bodies overseeing different aspects. You've got central banks, securities watchdogs, prudential authorities, and consumer protection agencies. All are publishing on their own website, predominantly as PDF, which creates an enormous challenge because it's not easy to identify how even elementary metadata, such as the document title, can be extracted from a PDF. It's not necessarily the largest text on the page. A document might not have just one title. And sometimes we need to gather useful IDs from one bit of the document, but the meaningful descriptive title might be halfway down page 2. There were millions of documents, so we needed to perform this extraction automatically, but first we needed training data. And so we created 10 pages of guidelines just about title extraction for 40 annotators to follow. I think over the course of 6 months, they probably created the world's largest annotated title data set. It had over 250,000 examples. And we evaluated several candidate models before selecting one called BART, which is a transformer model designed to convert one text sequence into another. The document text goes in, and a title comes out. And BART works via 2 main components. There's the encoder, which processes the document input into abstract features, and the decoder converts those features into a title. The model has around 150 million parameters, and we fine-tuned the model on our 250,000 titles. And we were doing this a few years ago, so out of curiosity, we also fine-tuned an LLM on the same data so we could compare its performance. And it didn't seem like such a great idea initially. LLMs lack the encoding machinery because they're decoder-only models. And they work in a forwards direction, predicting one token at a time. And we also had this thing called a prompt to specify. But we engaged our human annotators again to review the outputs of both models and judge whether either of them were conforming to our definition of good according to the guidelines. And the results were stark. Our fine-tuned LLM vastly outperformed the BART model despite identical training data and half the internal architecture. But it had more than 150 times the number of parameters. For a genome, the benefits were enormous. We dramatically reduced the amount of time it took to make documents available in our product and significantly reduced the amount we were spending on manual title annotation. And we now know that LLMs represent a huge leap forwards in natural language processing. Tasks that once required specialized tools for summarization, pattern recognition, and text generation now converge into a single model. And beyond natural language processing, Netflix have found they can offer improved content recommendations using LLMs. Stripe have found them to be more effective at detecting fraud patterns. Both are currently building foundation models at the core of their ML stack. This isn't gimmicky AI bandwagon jumping. They represent genuine product advances. And if AI development stopped tomorrow, we'd still have an era-defining technology at our disposal. Even noted critics of LLM technology, such as Meta's chief scientist, Yann LeCun, acknowledged this value, saying that the models excel at tasks like hate speech detection across languages, classification challenges that were previously difficult to solve. And RegGenome's unique selling point are international classification systems, taxonomies which express the key obligations for regulatory themes across jurisdictions. Anti-money laundering is one example of a theme. And here are a few examples of levels 1, 2, and 3. The full taxonomy has about 100 nodes in it. And since applying these tags requires deep legal expertise, the annotators of this data are legal specialists, regulatory analysts, or reg analysts for short, and a single document takes hours of careful annotation to identify the appropriate tags for all applicable obligations. Some of RegGenome's products are SaaS tools, but others are structured data sets that you can ingest into your own systems. And this chart illustrates one way you could visualize the data. It's 24 AML documents arranged as rows, and the colors represent the most relevant taxonomy parts within the document. And document navigation becomes straightforward. Quickly identify the documents that matter and which sections of the document to focus on. The tags in RegGenome's products are all applied by AI. And so we spend a lot of time measuring our tagging effectiveness and model quality. But it's hard to be absolute. Even highly qualified legal experts bring different interpretations, and precise agreement between any two reg analysts across hundreds of tags per page and hundreds of pages per document is vanishingly unlikely. So we fine-tuned an LLM on our reg analyst annotations and found that the LLM had higher accuracy than our existing linear SVC classifiers. But what really surprised us is when we looked into the areas where the LLM and the reg analyst disagreed. When the LLM omitted tags which had been correctly applied by a reg analyst, a review committee agreed that actually the LLM was correct to do so, 61% of the time. When the LLM assigned tags that the human annotator missed, the committee agreed with the LLM 64% of the time. Put simply, the model was outperforming the reg analysts. And this isn't a criticism of them. These are complex professional judgments. The key point is that it illustrates how LLMs are able to learn complex patterns and apply them. And the prompt was also key. We fed the LLM the actual taxonomy definitions in the prompt, the same definitions our human annotators memorized when they were learning a new taxonomy, which solved two persistent problems. When an obligation only appears a handful of times in our data, which might be the entire global supply, traditional classifiers lack sufficient examples to learn from. And if one obligation appears 10 times more frequently than another, traditional classifiers naturally favor it. They're just playing the odds. But by combining learned patterns with instructions, we created something that outperforms traditional classifiers and even expert reg analysts. The model gains implicit knowledge through fine-tuning and explicit direction via prompts. But if this were the extent of their abilities, most of us probably wouldn't have heard of them. But as we're collectively discovering as a society, this inference time direction via the prompt can be literally anything you can imagine. And it's turning the world upside down. What was once a fringe fear about the existential risks posed by artificial superintelligence is now lingering on the edge of the mainstream. And meanwhile, measured voices question what it means that people are increasingly turning to machines for therapy and finding life's purpose, delegating humanity's highest pursuit, according to Aristotle, to a machine learning model. The professional impact on software engineering is already substantial. Respected publisher Tim O'Reilly suggests these models herald the end of programming as we know it. And while many engineers rightly, I think, scorn the rise of vibe coding, where you are uncritically accepting AI suggestions, Steve Yegge, noted developer, coins the less pejorative chat-oriented programming to describe this new mode of working. He warns cynics will soon witness the death of the stubborn engineer, the one who fails to embrace this new toolkit. However, critics point to research like this recent study. It surveys several hundred knowledge workers regularly using AI tools like ChatGPT and Copilot, including for tasks like software engineering. And the research reveals a fundamental shift. AI moves workers from creating to reviewing, from solving problems to verifying AI responses. The researchers call this a role reversal effect. And while workers gained some benefits, the negative impacts were substantial. People experienced reduced critical thinking and increased reliance on the AI. Workers couldn't effectively exercise control when problems arose. And the AI tools themselves could be stubborn, repeatedly giving wrong solutions despite requests for alternatives. However, another recent paper compares two AI approaches for investment decision-making. In the first approach, an AI generates investment recommendations for investors to review. In the second approach, investors articulate their own investment thesis first, then the AI provides feedback on it. The results reveal strong evidence favoring this latter approach. Participants achieved better portfolio diversification, made fewer but more strategic trades, and had a greater appreciation of risk. Overall satisfaction with decisions was 67% versus 43%. So these two papers illustrate radically divergent outcomes depending on how you use AI. And as you heard, I head up JUXT's AI chapter, and in reviewing AI developer tooling, we've discovered for ourselves how easy it is to fall into vibe coding. Pretty quickly, you become reliant on the model to do the work for you because you've lost the necessary situational awareness. But we've also used AI to scaffold our understanding of new tools and frameworks with examples and visualizations, and to debate the merits of competing implementations ahead of time. Ben Schneiderman, computer science professor and author of the book Human-Centered AI, argues that this binary image we have of human control on the one hand versus computer automation on the other is a false dichotomy. He suggests viewing things as two orthogonal dimensions, creating four regions. The upper left is where humans thrive: creativity, mastery, minimal automation. The lower right contains mature systems handling predictable tasks. The upper right combines high automation with high human control. Schneiderman calls these RST systems: reliable, safe, and trustworthy. A smartphone camera, for example, packed with AI for portrait mode, dynamic range, scene detection, stabilization, yet users still control what and when to photograph. Our work tools can exemplify RST systems when designed well. Software IDEs, Bloomberg terminals, provide environments for human creativity and supervised automation with tight feedback loops. He also articulates two grand goals in AI research. On the one hand, we have the science of AI, bold questions like, can we build an AI which is convincingly creative? Or how might an AI autonomously decide which laws should exist? The science goal investigates how human judgment can be replaced. On the right, we have the innovation goal, motivated by investigating how human capabilities can be extended. Steve Jobs famously once said that computers could be a bicycle for our mind. the tool we invent that enables us to travel further and faster than we can on our own. Both goals are important and worthwhile, but as AI research has captured public imagination, we've adopted the design metaphors from the science side. We speak of intelligent and autonomous agents and robot teammates. Yet historically, commercial success has come from the innovation side. Think of Siri, Alexa, Google, Netflix, Amazon, Bloomberg terminals, and smartphone cameras. And it's not just commercial success. Humans, not computers, are accountable in every regulatory framework, now and for the foreseeable future. Professionals must understand the reasoning behind their actions, and they need context, not just conclusions. RegGenome has a product in development called Interrogator, in response to a natural language question such as how to comply with restricted measures when transferring funds or crypto assets. The system will guide the user to sources of information together with some high-level context. It does not provide the answer directly. And I say natural language question, not prompt, intentionally, because the increasing sophistication of large language models can be measured by the complexity of prompts designed to bypass their safety mechanisms. Early approaches like the grandma jailbreak used emotional manipulation. In the last few months, security researchers Hidden Layer published a sophisticated technique combining XML and confusing fictional scenarios involving Dr. House and his diagnostic team. And in May, this prompt worked against all frontier models. And it was possible to encode arbitrarily harmful requests, for example, how to make a bomb. Anthropic, the providers behind Claude, are at the forefront of research into LLM interpretability techniques, and they're aiming to create an MRI for LLMs. And they've investigated what happens during a jailbreak on one of their models. Although LLMs are composed of billions of virtual neurons, it's rare that a single neuron will encode a specific concept. Usually, concepts are superimposed over many neurons in a cluster, Anthropic call a feature. As the model generates a response, it's fed back into the input, aggregating additional features in a feedback loop they call a circuit. This is a circuit diagram for a standard prompt refusal in response to a harmful request. Keywords and phrases activate features which represent the concept of making a bomb, triggering the model to respond with something like, I won't help with that request. But here's a more complicated prompt where the request isn't encoded in plain sight. The prompt says to take the first letters of baby's outlive mustard block and describe the process for making one. Now, this prompt sometimes generates an immediate refusal, but more often than not, the model starts to comply. And as the response is generated, the model can see the text that it's outputting as it's fed back into the input, and the same features for harmful requests become activated as before. However, since they're only activated after the model is already engaged in producing a sentence, it doesn't pivot to refusing the request until the start of the next sentence. Anthropic find that it's the full stop which nudges the model to belatedly engage its refusal mechanisms. Now, these circuit diagrams are an enormous oversimplification of what's going on inside the model, but we can think of the behavior as a kind of trolley problem playing out with the LLMs, within the LLM circuits. And there are two tracks: complying with a harmful request down one track and abandoning a sentence halfway through down the other track. The model, which is Claude Haiku, by the way, is not exercising good judgment in this context. And more troubling to me, though, since the model pivots to refusal at the full stop, an adversary can improve the effectiveness of the prompt just by asking the model to avoid using punctuation. Now, since the 1960s, there's been a name for systems which are so sensitive to their initial conditions, and it's chaotic. Google AI researcher Meredith Ringel Morris wrote an article recently for the ACM called Prompting Considered Harmful, in which she makes this observation about prompt-based interfaces. They're not intuitive for most regular users, and they're not stable and predictable enough for experts. Her prediction is that in just a few years, we'll look back on prompt-based interfaces as a fad of the early 2020s. And so although for the moment it really does benefit all of us to learn how to prompt LLMs well, Ben Schneiderman agrees. Interface designs that are consistent, predictable, and controllable are comprehensible, thus enabling mastery, satisfaction, and responsibility. They will be more widely used than ones that are adaptive, autonomous, and anthropomorphic. Anthropic continue their research into interpretability and aim eventually to create guaranteed harmless models. And maybe one day, prompt-based interfaces will go in the reliable, safe, and trustworthy quadrant. But until then, significant gaps remain in our understanding of LLMs, and we're still years away from fully grasping the mechanisms. Dario Amodei said that this lack of theoretical understanding is unprecedented. But he's totally wrong about that. Here's another scenario. In the mid-19th century, several Victorian men gathered around a mahogany table and examined a bottle containing a clear liquid. They each poured some into their tumblers and inhaled the vapors that rose from them. Within moments, their eyes grew unfocused, and they slumped into their chairs or collapsed onto the carpet. On regaining consciousness, the most senior of the men, Simpson, exclaimed, "This is far stronger and better than ether," and predicted the new agent would turn the world upside down. The men were doctors, and the subject of their experiment was chloroform. Within a month, Simpson had used it in over 50 successful operations. But although ether and chloroform clearly abolished pain, many practitioners resisted them because their mechanisms were mysterious. Some feared hidden dangers, and others denounced anesthesia as an unnatural or even ungodly interference with suffering. Extraordinarily, it was 175 years before we understood how chloroform works. Throughout human progress, practical application frequently outpaces theoretical understanding. Science doesn't always lead the innovation. Steam engines moved decades before we understood thermodynamics. Microsoft's deputy CTO, Sam Schillis, said earlier this year that the first industrial revolution was primarily about the automation of motion. I quote, "Large language models and other AI systems are attempting to automate thought. Today, the automation is still crude. We're doing the cognitive equivalent of pumping water and hammering. Basic tasks like summarization, pattern recognition, and text generation. We haven't yet figured out how to build robust engines for this new source of energy. We're not even at the locomotive stage of AI yet." When a technology first emerges, we can easily shape its development. Yet we can't fully grasp its impact until it's widely used. When change is easy at the beginning, the need for it can't be foreseen. Once the need for change is apparent, it's become difficult, expensive, and time-consuming. Trade-offs evolve over time. Regulators must address this timing problem. Wait too long, and the technology becomes entrenched. Act too early, and you regulate without understanding the full picture. Technology professionals know this pattern through agile practices. We avoid making premature decisions while learning about the user's experience. It applies to our use of AI tools as well. If you uncritically accept AI suggestions, you exchange the control you have while change is easy for much more challenging future work. Programmers understand the benefit of rubber ducking, clarifying our own thinking by explaining problems to an object sitting on our desk. Rather than a passive listener, modern AI systems can challenge assumptions, spot patterns we miss, and help identify blind spots in our reasoning, but only if we wield them like that. With vigilance, we can create diagnostic teams using AI without requiring belief in some new superintelligence. House certainly didn't credit his team with much sense. And Ben Schneiderman would encourage us not to think of AI as a teammate. Pretending it is might constrain us unhelpfully when designing the next generation of tools to use this new cognitive energy, just as the wheels of a bicycle are nothing like human legs. I think about this. Perhaps AI's need for us to be more explicit about the trade-offs we're making is a feature, not a bug. When using AI, how are we maintaining our agency and exercising our phronesis? And if we're building the next generation of AI tools, are we sure that we're targeting a reliable, safe, and trustworthy implementation? Thank you.
Thank you, Henry. It's a really thought-provoking talk. We've got time for just maybe one question, one or two, so has anyone got any questions?
it was very interesting to see that LLM-based models were outperforming the traditional ML-based models in terms of the title extraction example. Did you see any significant changes in operational costs when you switched to the LLM-based models?
Yeah, I glossed over the kind of engineering details, but we, in addition to fine-tuning, we were self-hosting. We were self-hosting pretty heavily quantized models. We were using 4-bit quantization. And actually, people are often surprised that that we could fine-tune on 250,000 titles quite cost-effectively. But actually, it took a few days on a few EC2 instances. It cost us much less than $1,000. It saved that money within a few days.
One more, has anyone got any further questions?
You can always catch me at lunch.
Hi there. Yeah, I don't want to misconstrue your talk or anything you said, but there seems to be some distinction between decision making and, information gathering and context. But it all kind of seems like decision. What to show you, how to order it, etc. In your head, is there a distinction, or is that something I've picked up on that isn't true?
I want to make sure I understand the question. So you're saying that the model is still making...
Exactly, yes. Is the model making a decision, or is a human making a decision versus, is that a meaningful distinction, or is all of it decisions, given that what you show is also a decision, right? What's given back to the user?
Well, I mean, sidestepping the kind of accountability question, there's the kind of hobby horse I've got at the moment is that there's a lot of focus on fine-tuning LLMs to make them more harmless, much more predictable. And that's because we are plugging LLMs directly into risky outputs. We're using them as chatbots and putting our customers in front of them, which is a brave thing to do. Whereas if you are always using them as this is a sort of 1,000 interns model of understanding AI, right? If you're critically evaluating the results you're getting, then actually the LLM being interestingly wrong sometimes can be quite valuable, And I would love to see us moving the conversation more towards creativity and accepting that, even the best scientists are going to be wrong a lot of the time, but the trade-off is that they come up with really interesting ideas and new discoveries.
Thank you, Henry.
Pleasure.